The central white sphere represents Earth or any massive object. Around it, you can see a network of white nodes connected by colored arrows. This is our tensor network, a mathematical structure that represents the quantum information relationships in spacetime. The blue arrows pointing toward Earth represent what we call the A parameter, or asymmetry factor. This creates a convergent field that pulls inward, similar to what we experience as gravitational attraction. The green arrows pointing outward represent the R parameter, or restoration rate. This creates a divergent field pushing outward. What's fascinating is that each node cycles between these two states, sometimes exhibiting convergent behavior, sometimes divergent. This cycling represents the dynamic nature of quantum information exchange in spacetime. Notice how the network becomes denser near Earth. This is a key insight of emergent gravity theory. The tensor network density increases in regions of higher gravitational influence. In conventional physics, we'd say spacetime is more curved near massive objects. In emergent gravity, we interpret this as information becoming more densely entangled near mass. The strength of gravity in this model is determined by the product of our two parameters, G = AR. When the asymmetry factor and restoration rate interact, they create what we experience as gravitational force. Inside Earth, you can see both blue and green arrows mixing together. This represents the complex interaction of these fields within matter itself, where both convergent and divergent processes occur simultaneously. One of the most important aspects of this visualization is the bidirectional flow. Watch carefully, and you'll see that nodes don't just send out arrows, they cycle between states. A node will send blue convergent arrows toward Earth for a while, then gradually transition to sending green divergent arrows outward. This cycle continues indefinitely. This bidirectional behavior represents a fundamental aspect of emergent gravity theory, the constant exchange of information between spacetime points. Gravity emerges from this ongoing process of convergence and divergence, creating a dynamic equilibrium that we experience as a consistent gravitational field. The slow animation speed allows us to carefully observe these transitions and appreciate the subtle dynamics at play. While the visualization is intuitive, it's based on sophisticated mathematics. The tensor network represents entanglement entropy between time. Eric Verlin's theory proposes that gravity emerges from the entanglement structure of quantum information. When matter is present, it creates an asymmetry in how information is distributed, leading to what we experience as gravitational attraction. The A parameter, shown as blue arrows, represents the concentration of baryon asymmetry, essentially how matter creates information asymmetry in the quantum structure of spacetime. The R parameter, shown as green arrows, represents the rate at which local symmetry is restored, how quickly the system tries to return to equilibrium. Together, these parameters create a dynamic system that produces effects identical to what we call gravity, but without requiring gravity to be a fundamental force. This theory has profound implications. If correct, it would mean gravity isn't fundamental, but emerges from quantum information dynamics. Similar to how temperature emerges from the collective motion of particles, emergent gravity makes several testable predictions. It predicts slight deviations from general relativity at very large scales. It provides a natural explanation for dark matter effects without requiring new particles. It suggests connections between gravity and quantum information theory. Recent astronomical observations of galaxy rotation curves and gravitational lensing provide intriguing evidence that supports some aspects of this theory. Though much research remains to be done, our visualization includes several interactive controls that let us explore different aspects of the theory. The simulation speed slider lets us adjust how quickly the animation runs. The density sliders control both the overall network density and the concentration near Earth. The display options let us show or hide different field components. These controls allow us to focus on specific aspects of the theory and better understand how the different components interact. The tensor network visualization we've explored today offers a window into one of the most exciting frontiers in theoretical physics. Emergent gravity challenges our fundamental understanding of space-time and gravity, suggesting that what we experience as gravitational attraction may actually emerge from deeper quantum information processes. Whether this theory ultimately proves correct or not, visualizations like this help us build intuition for complex physical concepts and inspire new ways of thinking about the fundamental nature of our universe. Thank you for watching. If you have questions about emergent gravity or this visualization, please leave them in the comments below.